Now I would like to do one thing that is a little bit confusing. I said so far there was a global statement of what's a symmetry. So global statement of what a symmetry was global both in the group transformation and in time. If I go some finite distance and I rotate some distance, which is big, I go from here to India. And then I do my experiment and I come back. I get the same result. So this is global. Then I told you that there is also local. So I told you that one way of thinking of invariance is that I take my law of motion, dynamical velocity field, this tangent here. This is the local velocity. It's defined every place on this. It's the same one up to transformation. But if I choose another moving frame, I might have another velocity. This whole trajectory is specified by specifying V. And I told you the idea is that if I do this, I have law of invariance. I'm invariant the symmetries because law hasn't changed. This is local in time. This is vector field that happens instantaneously in time. It's global in space. And obviously that's unnatural. What I really need is I need local, both of them local. So what you do is you study what happens if I write G transformation, small transformation as identity in d by d dimensional space plus this small transformation, and I drop the rest. So just substitute it here. And obviously you'll have to do one partial derivative because I'll have to Taylor expand this thing. So this is I, j, and this is matrix multiplying vector. So when you do that, you get a very simple result. It says that the tangent in the group direction, so here is a tangent to this surface. So if I move this way, I stay in the group manifold in linear approximation. So tangent in the group manifold of the velocity, this came from this term multiplied in V. Let me explain. The tangent, again, is always defined the way you would define angular momentum. So tangent of A is you're at point X and you rotate it by the matrix T in direction A. And there are n independent directions for group parameters, these capital N parameters. So the statement is minus A, where A's are all Franz stability matrix equals 0. So this is a local statement of symmetry. So the global one you understood, this picture you understand really well. I do this, and then I rotate, or I rotate and do this. Now this is a statement that's natural. This is defined, remember, this T A of anything, but in this case V is defined as generator of the group in direction A multiplying whatever this thing is. So this guy is infinitesimally turning the velocity around. So now Sophus Lie was no dummy. So this is the first thing he did. So this is called the Lie derivative. You people, of which I know at least two, who have taken good courses in differential geometry, helped me rewrite the book, because when I write it as a Lie derivative, it just looks ugly. So the idea of Lie derivative is that you want to compare what happens if you vary something in this direction and then do it that way, versus you vary it in this direction and do it that way. This is a way to measure curvatures of spaces, etc. You compare two paths, and if space is flat, you get 0. But if space is not flat, then you get something, and the result is called Lie derivative. This tells you what the essence of the local curvature of the space. And in our case, Lie derivative is trivial because moving in one direction and the other direction, so moving in kind of x direction, but you have to account for the shear because you did the Taylor expansion of this term in here, is the same as moving the velocity. And I don't find this formula intuitive. The original formula is totally obvious to everybody. This one, it's a formula. Now this is a very useful formula for you because very often it happens that you haven't noticed that your system has a symmetry. It's actually not so easy to discover symmetries. You know, if you write it from a symmetry principle, that's trivial because you want it to be symmetric and it is symmetric. So I want it to be length preserving. But suppose you're doing some problem in condensed matter physics, you're looking at some kind of, gases, lattices, electron gases, and do calculation and the result is symmetric and you have no clue why. There could be all kinds of hidden symmetries that could come from dynamical laws. You don't realize they're there. So this would be a test. So basically whenever you write your equations of motion, to make sure that you really have the symmetry in your equations of motion for a dynamical system, do this test. This is much easier than looking at global things because this is just depends on this matrix T, which is very easy, and you already have the stability matrix because you're computing it all the time. So you have all the stuff, and your law is given as velocity. So make sure that system is symmetric, or discover a new symmetry and publish an amazing paper. It's only rotations of a circle. It turns out, because it's nonlinear dynamics, this circle is one hell of a circle. That we'll see the next time, and we'll discuss one method of how to slice through this mess and get a piece of sliced bread that is nutritious for your mind.